Good morning, dear student, and welcome to this 32nd edition of our numerical method 2 class. I hope you enjoy your weekend, and I wish you all the best for this new week. Yes, Kashupi, apparently you have a concern. You have the floor.
Yes, sir. I have a question about the test. Are we only having two tests, test one and then a comprehensive test?
No, there will be test two. Test
Uh-huh.
two by Monday. Yeah? Let's say Monday next week. You'll be writing test two.
All right, sir. Thank you.
Yeah. So please, class representative, you can already announce. Why not this Friday? Is it too early? Okay, let's say next week Friday.
Yes, sir, it's
Next.
very
This
early.
Friday is too early.
Very
Okay,
early,
next
sir,
week
because
Monday.
on the course outline it does say that we only have one test and then the comprehensive test.
Two tests, comprehensive. You have two tests, comprehensive test, and assignment. A total of 4. Test 1, test 2, comprehensive assignment. That's 4 in total.
Okay, sir.
Okay, so let's quickly see where we stopped last time. Remember, I introduced the concept of Gaussian quadrature rule. And the idea, who can tell me, if you remember, what is the main purpose or the main difference between the previous method and the new one that we introduced last week? That is the Gaussian quadrature formula. Who can quickly tell us? If you know, please, without wasting time. If you know, please raise your hand. I'm checking. If there's anyone who knows what is the main difference, can you raise your hand? Nobody? Well, what is the main feature of the quadrature? I mean, the Gaussian quadrature formula. Why do we need it? How different is it from the Newton code formula that we encountered? I mean, that we tackled last time in the previous session. Who can say something? Nobody? So you mean that either you don't read or you don't pay attention? So far, nobody. Out of 8. Class rep, Nanona, tell us. What is the main feature of the Gaussian quadrature? I mean, yeah, Gaussian quadrature formula. If you want to compare it with the other formula, like the Newton codes, closed Newton code formula that we encountered, that is trapezoidal, the Simpson rule, that is Simpson and 3/8 Simpson Volz rule. What is the main difference? Why do we need? Because if you can answer this question, I don't really know. It means that you don't pay attention, you don't read, you don't watch the videos, you don't study. That's the only conclusion I can make from this observation. Because I stressed on it last time. I stressed, I explained, I went to the slide, I insisted. Welcome, Simeon. Kashupi, what is the main difference? Where? Can you tell us what is the main difference? Oh, Shona, say something. What is the main difference? If I ask that question during a test, are you telling me that you all get 0? Hmm? So, for instance, if you look at this, if I go back to these are the Newton codes, right? You can look at this. These are the Newton codes. I can even look, okay, let us even use this one, because here you can look at the formula with the degrees of precision. Here, if I look at the first rule, which is the trapezoidal rule, the degree of precision is 1. Number of function evaluation, 2. Okay, function evaluation, so I will write here I will call dp for the degree of precision. One, function evaluation. 2, you have F0, F1. Degree of precision, three. Function evaluation, 3. Degree of precision, 3. It's still Simpson, even though it's the 3/8 Simpson rule. 3. Function evaluation, 4. One, two, three, 4. 1, 2, 3. So what can we realize? If I compare this, this is less than that. This is equal. This is less. So degree of precision is less than or equal to function evaluation. And in most cases, it is even less, right? That's why I say less than or equal, because equal for the Simpson rule here. That's the observation. So the degree of precision is less than the function evaluation. Number of function evaluation.
Sir?
And here, if we come here, degree of precision is 5. Function evaluation, 1, 2, 3, 4, 5. 5. So you see, it still falls in there. Good. Now, if I move from here, and look at the motivation here. When we talk about
There.
Can you talk?
We can't see your screen.
You can see my screen.
Yes, sir.
Can you see it now?
Yes.
Okay, so let me go back. So this is what I was talking about. For the Newton code formula, we have this degree of precision, number of function evaluation. They are all there. So you can see here 1, 2, 3, 3, 3, 4, and here you have 5, 5. So the general remark is that the degree of precision is less than or equal to the number of function evaluation. Right. So that's what we have for the Newton codes. Now, if I come back to the motivation of the Gaussian quadrature formula, here, this is what we have. The degree of precision obviously, if you have n plus 1 point, the degree of precision is this. But we are going to see, yeah? We are going to see yeah? Here. We are going to see. So you can see that the number of function evaluation, the maximum, if you look at this, the maximum of the number of function evaluation is n plus 1, if you look at this. Because this is the general. This is a general formulation for a Gaussian quadrature. I mean, not Gaussian, but at least for a quadrature formula. The maximum of number of function evaluation is n plus 1. That's the maximum. It might be less, but the maximum will be n plus 1. But here, the degree of precision, you can see here, is 2n plus 1. So you can see that the degree of precision here, in this case, we can draw the conclusion that the degree of precision is strictly greater than the number of function evaluation. Because here you have 2n plus 1, whereas here you have maximum is n plus 1. So you have this. Whereas previously we saw that it is less than or equal to the number of function evaluation. But here with the Gaussian formula, we see that the degree of precision is strictly, is almost the double. Okay, so that is just a recall of what we did last time. And we also saw that we derived the three-point quadrature rule. We derived this. We use the method of undetermined coefficient to find the weights. So we did this in detail last time. And I asked you as a homework to do the 2 point, because 3 point is even more complicated. We use three point, but I asked you to use 2 point to derive the 3-point quadrature rule, Gaussian quadrature rule. That's what I asked you to do, this one, homework. I hope you did it. Okay. Now, as a general remark, you will see that the limit of integration so far is fixed to -1, 1. You can see clearly that we use the interval -1, 1 to derive the various formula. The 2 point and the 3 point. We use that. But we also saw that we can convert if we want to integrate, because numerical integration is not reduced to an interval starting from -1 to 1. We have an arbitrary interval AB. Now, how do we integrate from AB knowing that we have a formula from -1 to 1? Because that's the purpose of this change of variable. Because you can derive, we have the 2-point rule here, derive from the interval -1, 1, and the 3-point from -1, 1. And we will even see that there is a general formula for any number of points, because that's where we will conclude with this one, the Legendre polynomial. We can still use the same, a similar procedure. You can see that here, all these polynomials are defined on the interval -1, 1. And you can use this formula to generate the Q. Remember, we said that for a Gaussian quadrature formula, we need Q. We compute, once we have Q, we compute the roots of the Q. The roots of the Q will give us our nodal point. And from that, we can compute the weights using the method of undetermined coefficient, or you can integrate we call them Lagrange or cardinal function. If you integrate them, it will give us the weight, or the method of undetermined coefficient. So still, the interval is -1, 1. -1, 1. Now, if we have an arbitrary interval, how do we transform our interval from -1, 1 to AB? This is the solution. The answer is here. You use this change of variable to do that. And if you do that, this is the formula that you get for the 2-point rule, and this is what you get for the 3-point rule. Please, I'm drawing your attention on this. On the slide, for the 3-point rule, you have B minus A here. Please change that. It's not B minus A, it is B plus A. Please change that. You can see here in green, plus. It's not negative, but it's plus. We should change it. Please do that. Okay, but what we are going to do now is to use this change of variable with a 2-point and 3-point Gaussian rule and see that actually this is what we will obtain, right? Instead of telling you that this is the solution, let us do that together. Because by so doing, the formula will be remembered. So let me quickly take so we have our 2-point Gaussian rule, which is the integral from -1 to 1 f of x dx, which is approximately 5/9. Oh no, for the 2-point, sorry. That is the 3-point. So for the 2-point is f of -1 by square root of 3 plus f of. Now for the 3-point, (5/9) f of negative square root of 3 by 5 plus 8/9 f of 0 plus 5/9 Okay, maybe a quick remark. If you look at this, you know already that these two weights are the same. This one, this, and this. And the function that we evaluate, here you have the negative, and then there is positive, the same root, square root of 3 by 5. And in the middle, you just have 8, 9, f of 0. Obviously, here the weights are the same, 1, 1, and then you have a root and it's negate, right? They are always present. And that's the same remark for an arbitrary degree. I mean, when I say degree, I mean the number. If you take n point, if n is even, you have all the roots and they negate, they will be present. But if it is odd, 0 will be one of the roots, and then you have negative, roots and they negate, right? On both sides, always like that. That's a general remark. It's a general remark. Tutorial. Have I released it? Yeah, I think I released tutorial 2. Huh? Yes, I released tutorial 2. If you look at tutorial 2, surely I didn't give the list of all of them. But if you take any numerical method book, numerical method textbook, look for the Gaussian quadrature rule. You will see there's a list. There's a list of all the roots because those roots are obtained from here. You can even write a program. That's why I encourage you to learn programming. You can write a program. You can write a program. If we have time and if you're interested, we can do that over a weekend. Please let me know if you're interested. We can do this. We can take this formula, program it, and say, for instance, for a given value n, it will give us the roots. You can do that with Python. You can do that with Python. You take this formula because this is the formula that will give you for a given n, it will give you the polynomial q. Remember that we need to determine q. But now this formula gives you the q. You don't need to integrate the way we did in class. This is the formula. We will come back to this by the end of the class. I hope we have time. Normally we are supposed to do that. And I apologize also because we were supposed to have a class on Friday. Because of your elder brothers, those people who are doing masters, they are your elders. They were making presentation, so I had to attend. So that's why. And I promised that I will be recording, but which I didn't do. I'm sorry for that, and I hope. Anyway, I'll have to catch up. If I don't cover this, I'll be compelled to have an extra, maybe after this class. If you are busy, I will record another one, but to cover this, I will need to catch up. In fact, I owe you even 2 hours because there was another Wednesday. But I will catch up, don't worry, I will catch up. So, as I was saying, the Q that you know, remember we have to integrate, it's too long. You don't need to do that. In real life application, if you need to find the Q, you just come here, write a program, you just say, n is equal to 5, for instance. If you want a 5-point question rule, the program will go and it will compute the polynomial for you and it will put it in your face like this. This is a polynomial. Now you say, I want the root. It also comes, it gives you. Don't be scared, it will give you. So that is the power of numerical programming. And as I told you, as I mentioned earlier on, if you take numerical method textbook, you will see the roots are given. If you want n equal to this, they give you a list. Let me see. Even if I show you the textbook, will you be able to, wait. Let me see if I have a, but that would be a waste of time. Anyway, for another day. So if you're interested, as I said, let me know so that we organize. For those who are interested, and not all of you. For those of you who are interested in learning programming, I can organize programming session over the weekend. to really take you through Python. Things like this, we go through and teach you how to do that. It will be helpful, it will be beneficial. So I encourage you. Anyway, I think I will need to ask you to fill a list, right? You put your name in a list, those who are interested. Then we'll be organizing a programming session for those who are interested. I will do that anyway. It's in my plan, no? It is in my program, no? I will be doing that. For those who are interested, it's not a must. I mean, it's not mandatory. It's not compulsory for you to be there. Those who are interested, for me, it would be like community engagement. I would take it like community engagement. That is, I commit myself to help the community. The community doesn't know how to program. So how do I help them? Okay, so let us do this. So what was I saying? I was saying that. Okay, so this one. So I want us to derive this formula, and we are going to use this change of variable. I already told you. Okay. Let me do this. There is something that I also skip. I said we use the change of variable x equal to. I think I asked you to do that as a homework. 2t minus b plus a by b minus a. That is our change of variable, and we use that to convert the integral from AB. This formula, I'm talking about this one. Right. I explained this last time. I explained. Okay, now let's derive these two formulas, this one and this one. That's what we are going to do now. Those who just joined or who joined late, I said that next week, Monday, there will be test 2. So inform me the other classmates. Okay, so we did this. Okay, this is a method of undetermined coefficient that we covered last time. Okay, now let's use our change of variable. So I will call this Gaussian. Oh no. Formula or rule? Okay, so we saw that the 2-point Gaussian rule. So you see that here we use the integral from -1 f of x dx. This is approximated by f of -1 by square root of 3 plus f of okay, so and now the 3-point Negative 1 to 1, f of x dx is approximated. So if you remember, you have 5, 9, which is repeated twice. You have it here, and here you have 8, because you just add 3 to this one. You have 8, 9 here. With f of 0 here. And then similarly, 5, 9, f of the opposite of what is here. Right? Because here you have negative. Remember, you have a square root of, I think it's 3 by 5. Yes. Okay, now, what do you see here? This 3, you have here 3, you have 5. This 5 is the same 5 that you have here. You have here 5, 5. And you add this 3 to 5 to get this 8. Are we together? That's how it's a way for you to remember the formula. It's not witchcraft. It's just a technique for you to get the formula right. Nobody taught me that, but I was inspired. Well, when I look at something, I think, how can I? It's a copyright. You need to pay me Vambo chicken before you use my formula or my technique. So I have 3, 5. This 5 is there. You see, remember 5, 9, 5, 9. And this 3, you add 3 to 5 to get this 8. So you have 3, 5, 9, 3, 5. You add that to get an 8 at 0. So you have this. You have the negative of this and itself there. Easy to remember. So those are just simple techniques for you not to cry. It's difficult. Okay. Okay, so, okay, now change of variable. Change of variable. Now we are going to change the variable to convert. Okay, change of variable. So we are going to use this change. We are going to use, because we want to convert. We want to convert from x in the interval negative 1, 1 to c in the interval AB. Right. You can derive that yourself, but we will not do that, right? But you can write the formula for yourself. How do I move from here to there? You can do it. Okay, but let us just give you the formula. So this will be 2t minus b plus a. You can derive this for yourself, divided by b minus a, like this. And you can check for yourself that if t is a, it will give you negative 1. X will be negative 1. If t is b, it will give you 1. So this is our change of variable. And we are going to use this change of variable to convert our integral, or to write our integral from a to b in terms of the integral from -1 to 1, because this is what we know and we want this. So we write this in terms of that, right? Because you can see that when you derive, it's always from -1 to 1. Even if you use the Qn, the formula that I indicated, x will be in the interval -1 to 1. Now, if you want to integrate from a to b, you have to know how to proceed. So that's the purpose of what we are trying to do now. Okay, now, if you use that change of variable, it is obvious, right, that the integral, will be able to write the integral in this form. So this one, I'm asking you to do this as a homework. In fact, I already asked you to do that last week. Those who did it were rewarded, because when you do it, you are rewarded by what you discover. For those who did not do it, I have nothing to say about it. Okay, so we integrate from -1 to 1. So meaning that we'll be using our, okay, because this is f of x, right? Here you have f of x, because x is from -1 to 1. It is x. If you look here, x is from -1 to 1. But we know that we can write x in terms of t. No, what am I saying? Because if you write t, t will be this one. So instead we write t in terms of x, because x is there. So you extract t from this formula. If you extract t from this formula, what do you get? You see that x here will be multiplied by b minus a, right? Because this is the denominator, b minus a. And then you will divide by 2, this 2, and you will send this to the other side. So let me write it here already. So if you solve for this one, you have t. T will be, because this is t, I first cross multiply, you have, and I will divide also by 2, this one. So I will have 1 by 2, which is the coefficient of t, and then I multiply by b minus a, right? And this negative, I will send it to the right hand side, to the left hand side, it will become positive, right? Because I'm all dividing by 2, so we have that, b plus a. So I take this and I substitute here. So f of this, which is b minus a x plus b plus a. dx, and you see that this x take the value -1, 1. Right. And now this one is your dt, because if you write dt, this will be 0. It will be 1 by 2 b minus a dx, and this 1 by 2 into b minus a is what you have here, this coefficient, and then dx, which is this one. All right, so this is the change. This is our formula for the change of variable. Now, for the 2 points rule, we are going to substitute. So this is our 2-point rule. I will do it for the 2-point rule, and you will see for yourself. So this is the 2-point rule. Now, if I substitute this into that, what do we get? So for the 2 points rule, so this implies that the integral from a to b f of t dt is equal to what? So I would take this 1 by 2 b minus a. Then I will multiply by all this integral. Now, what is this? If I take this, this is my, this is x. So this is my, because if I say f of x, so I will take this. You can see that x here, this is the value of x. I will take this x, substitute here in this formula, and take this x also. Let's call this x1 and this is x2. Right. So this integral, which is equal to this, how do I substitute it? So I take this, I come and substitute here inside, right? So this x is this one. So this will be f of this. So f of x1, I take x1 and put here. So that will be 1 by 2 b minus a times x1 plus 1 by 2 b plus a plus f of the same thing but with f2. Right, let me write it here. Now, what is x1? x1 is negative 1 by square root of 3. So I substitute there. So this becomes so I substitute that. This becomes f of negative. So I can put a negative here in front. Right? So that is negative 1 by 2 b minus a 1 by square root of 3 plus 1 by 2. That's the first one, plus f of the same thing, right? But with a plus, right? So for me to gain in time, I just copy this. Right, so that's what we have. So now if I expand that again, if I expand throughout, so I can say that this is b minus a like this by 2, right? F of I can just say here minus b minus a by 2 square root of 3 plus b plus a by 2. It's simpler like this. Plus the same thing, but with plus here. So plus So exactly the same thing. Or I can factor like this, or I can expand. It doesn't matter. It's the same thing. B minus A 2 square root of 3 plus okay, there's no need to factor because it's already there. So now, okay, so that's what we have. Now, if you compare this with the what we have in the note, so you will see that they are similar. Let me share the note. So you see that it's the same thing. You have b minus a by 2, b minus a by. Now you have here minus b by 2 square root of 3, and then b plus a by 2. And then you repeat the same thing, but without the negative here. It's exactly that. So it's exactly the same thing. So that's how you substitute. Okay, and now this one, as I mentioned, this you can see that this is plus. Why is it plus? Why is this plus? Why is this plus? Because of this. Because if your f of 0, because remember that this is f of 0, if you replace x, because remember x will be here, you put x here, 0. If you put 0 here, it will cancel out this term, and then the constant term will remain. That is b plus a by 2. So b plus a by 2. So that's why here you have the constant term, because x will multiply this part. Is that clear for everybody? Is that clear? If you don't understand, please let me know so that I repeat. I'm coming here, I'm saying if x is 0, you see that if you put 0 here, if you replace this by 0, you'll be left with b plus a by 2, right? What I'm saying, we are here. If I copy this, I am here. What I'm saying is that if I let in this formula x equal to 0, if I substitute x equal to 0, what do I have? Then you have this. So in other words, f of 0 is converted to is that clear for everybody? It's converted to f of b. So that's what I was saying, that in the notes, if you go back to the note, this should be plus this one, plus this one. You see the arrow, this one. For the 3 point, remember the middle term, this middle term, 8 by 9 into f of 0 will be converted into this with b plus a by 2. So you can proceed in the like manner into the substitution. You get exactly this long formula. Because you remember that you multiply any coefficient by b minus a by 2. So this 5 by 9 will be multiplied by this. So you have it here, 5 by 9. You see that the 9, this 9 will be multiplied by this 2. 9 by 2 becomes 18. That's why you have 18 here. I have b minus a as a factor. You have another b minus a here, and you have b minus a. Okay. Now, because here it is 8, and you have divided by 2. When I say divided by 2, it's this 2. Right? So this this 8, when I will divide by 2 here, it will become 4. So it will be 4 by 9 in the middle. 4 by 9. Because of the 2 and the 8 there, it becomes 4 by 9. And you have the rest. Now you have your f that will multiply your x. This is the x here. Negative square root of 3 by 5. And here, positive square root of 3 by 5. Multiply this, and you have the constant term, Now, when you come here for 0, 0 will multiply this, and then you'll be left with this constant term, b plus a by 2, which is this one. So it's b plus, so it's not minus, it's plus. Please make sure you change this on your slide or your notes. It's plus. All right, application. You have these two applications. I ask you to go through that. So this is the application, right? So now let me come back to this Legendre polynomial. If you recall what we did for our 3-point quadrature rule, this is what we obtained for our Q, right? 5 times x cubed minus 3x. That was a Q that we computed. And this is the Q. 5x cubed minus 3x. Now, that is for the 3-point. Now, if we take n equal to 3 into this formula, because here we have Q0 is 1, Q1 is x. If we want to take n equal to 3, we need to compute Q1 and Q2. Right? Now, let us come here. Let me write it. If n is equal to 3, that's for the 3-point, right? N is equal to 3. Now, Q3 x will be 3 times, that is 5 by 3, right? 6 minus 1, 5. And then we have x Q2 x minus 2 by 3 Q1 x. I know Q1, but I don't know Q2. So Q1 here is x. But I need to compute Q2. But already you have a Q2 here. This is Q2. Right? I assume that we did that. Now, if we take this Q2, substitute here, then Q3x will be equal to what? I just substitute this. Because to compute this one, you need what? You need Q1 and Q0. They are both here. You just substitute into that formula. Right? So I take that 3 by 2 x squared minus 1/2 minus 2 by 3 x. Right? Now I expand this. If I expand this, this will give us 15 by 6, right? X cubed right? Now minus 5 by 6 x minus 2 by 3 x. No, now already you have, okay, and then this is equal to, you see that this one is unchanged. That is obviously this one is a factor. Oh, I could have even, you see that this is 3, so it's 5 by 2. So this is 5 by 2, right? 5 by 2 x cubed, right? Now these two, you see I have xx there. Now if I add these two, this will be negative, right? I just multiply this by 2 again for the same denominator. So this will be 9 by 3, which is 3, right? Are we together? That will be negative 9 by, no, by 6, sorry. Negative 9 by 6. Negative 9 by 6, like this. But I can also simplify that by 3, because this is 3 by 3. So this will be 3 by 2. So 3 by 2 x, right? Okay, so that will be our, and that's what we have here. See, minus 3 by 2x. So that's how we compute. But now, what is this in terms of the Q that we computed in our rule? You can see this is what we have. So if I multiply this by 2, I have exactly the other one. I have this one, right? So here, if I multiply this by 2, 2 times q 3x is 5x cubed minus 3x, and this is the qx that we computed in the 3-point Gaussian formula or rule. So what is the consequence of this? To say that it's just a factor. So if you use any rule, the Q that you obtain by your method and the Q that this formula will give you, right? They will just a constant multiple of the other one. That's all. So the roots that you want will be the same. They have exactly the same root. So that's why with this formula given, you don't need to compute this Q any longer in your application. You just use this formula and you keep these two in your program, because you can write a computer program that would generate this polynomial and its root for you. So there's no need to go and do all those integrals and derive and all those computations. You need to know those steps for your understanding of the method. But in real life application, you don't need that. You'll be using this in your program. That's why you need to know how to program. Okay, we'll stop here for today. I hope you enjoy. Thank you for your kind attention. Is there any question before we stop? Okay, if there's no question.
Yes,
Yes, any question?
Is the test 2 online or face-to-face?
Okay, it will be online.
Thank you.
Okay, goodbye.